This is a joint work with Dr. Fracassi, Tom George, and myself. I'm a postdoc fellow at the University of Texas at Austin. And why are we discussing or looking at decentralized exchange? As you can see, it is taking market share away from centralized exchange. So it's kind of an interesting topic to look at. How do you compare two exchanges, decentralized and centralized exchanges? So we're going to compare trading costs here, and I want to give a very brief primer of what are trading costs. So think of trading cost as there are two components of trading costs. One which we call transitory price impact, and the other one is adverse selection. So think of what is a transitory price impact. Here we have a couple, they want to buy a house. So they have investments in stock and they want to pay for down payment. They are going to go ahead and give an order to sell their stocks so that they can get cash and buy down payment, for the down payment. They are not trading on any information. They just need liquidity. And liquidity provider is going to charge some cost associated, because now they have a big order they will sell. Liquidity provider is going to keep that order for a while, and then he's going to work his inventory out in a couple of hours or day or two, depending on what type of stock it is. So that's a cost associated with. There's a cost associated with it. These price impacts generally come back. That's why they're called transitory. So if a large order comes in, price goes down. It's a large order to sell, but then it's going to come back up. On the other hand, there are informed traders. Informed traders trade on information. A classic example would be somebody lives in a small town, it's a small cap stock, and suddenly finds out that the CFO has had a heart attack. And he knows that the price is going to go down. That information, trade through that information, is considered permanent, because price is going to go down and remain down until there is a resolution of what's going to be with the CFO. That is called adverse selection. Liquidity provider doesn't know that the person who's trading with me has information, and that is going to last for a while. So liquidity provider has to anticipate these two types of traders, and then they have to keep provision for that in terms of bids and offer spread. Now that we understand the two types of costs, we have two types of exchanges here also. We have a centralized exchange, which has the way it works is that there are stacks of bids and stacks of sell and buy. Liquidity providers have the ability to control how much volume they want to provide liquidity for and at what price. So they keep control. And then there's a matching engine that sets market orders, meets with buyers and sellers of the liquidity providers are providing. On the other hand, we have a Uniswap that goes by a certain formula, that certain smart contract, which ensures that at every turn, the product of the two tokens have a constant number, right? So here, liquidity providers are pooling their liquidity, and they give up control of at what volume and at what price they want to provide liquidity. We thought that this is an interesting, two different architectures, two different processes, and it will be interesting to see quantify trading costs in commonly traded pairs and find out what are the determinants and why liquidity providers are engaged in providing liquidity in these exchange Uniswaps pools. So for that, our research question basically are, what are the determinants of liquidity? Why people would provide liquidity in Uniswaps? Then we do an exercise to find out what's the magnitude of trading cost in Binance and how do they compare with the slippages, which is synonymous to the trading cost on Uniswaps. And then what factors affect these slippages. So these are the three things we discover, we identify in this paper. All right, so this is well, some of it is not clear, but this is the basic theoretical model. So we come up with a theoretical model. And I don't want you to be intimidated by this equation here, because I'm going to explain it clearly. We are creating a make-believe world. In this make-believe world, traders are, they are neither risk takers nor they are risk averse. So they are neutral. As long as they are getting fair compensation for the risk, they are willing to trade. They are suddenly endowed with certain tokens. So think of it as your uncle, your dad has given you a gift of tokens. Now you have two options in this world. Either you can sell those tokens on a centralized exchange like Binance, and there is a cost of selling, which I explained you earlier, and that is lambda, which is the combination of this transitory and permanent trading cost. Or you can post all these tokens and provide liquidity on a Uniswap pool. Now, everyone has a private valuation. The person has a private value of what he thinks or she thinks is the value of that token. So think of this equation as very simple equation in a way. Here is your E, which is your endowment. How much of that you will, if the second term, which is the subtracting term, if all of that is 0, all of that E will be posted as liquidity in Uniswap. So why would you not post liquidity on Uniswap? It will be if the V0, which is the price on Binance, is higher than your valuation, your private valuation. This term here, which is this term, expectation term, is basically like an average expectation of private values of everybody. So we are saying that if you can actually, your value, private value is lower than what you can sell it in Binance, a rational investor would sell everything on Binance and not provide any liquidity. On the other hand, imagine a situation where you have a very high private value of this token. In that case, you will not sell anything on Binance. You'll put everything in liquidity pool. We further define in this theoretical model, we define that this term, which is the expectation term, is proxy or equivalent to the reserve price on Uniswaps. Reserve price is a theoretical price on Uniswap, which is the ratio of numeraire reserve to the reserve of that Uniswap. For example, ETH to USDT would be the reserve price of how much ETH is posted on Uniswap and how much USDT is posted on Uniswap. So this is basically our model. So think about this as certain implications. By the way, this second term here is showing you the slippage and what slippage actually means. Slippage actually is, if you take the variance of slippage, it is equivalent to like the dispersion of private value. Remember I told you everyone has a private value, but if your private value is different than somebody else's private value, then that means there is a dispersion in private value. Whenever there is trading usually is done when there is dispersion in value. Otherwise, there won't be any trading. If everyone agrees on something, trading is not possible. Somebody has to be a buyer and somebody has to be a seller. So what are our model insights? First model insight actually is that if there is this term that Binance price is higher than the private average private value, I'm likely to post less reserves on Uniswap, right? Which makes sense, right? You're going to sell rather than you're going to post it on the liquidity. But that is net of lambda, which is the transaction cost on Binance. So higher lambda, if it costs a lot to transact on Binance, you are likely to provide more liquidity on Uniswap because your cost of selling on Binance is very expensive. So there is this interactive relationship. And so higher the difference between Binance market value or mid-market value and the private value, average private value, more likely agents will sell and not provide liquidity. On the other hand, if there is a higher trading cost on Binance, they are more likely to provide liquidity. And reserves are determined by interaction of these two terms. The other thing which I have not explained, but this, one of the insights that come out of our model is that slippage is invariant of trading cost on Binance. So these two markets are unrelated to the extent that slippage is not affected by trading cost on Binance. And the other thing is that variance in slippage is a proxy for dispersion, so it will tell us activity, what is driving activity in Uniswap, what is driving liquidity activity in Uniswap or trading activity in Uniswap. So with that, our challenge is to estimate trading cost on Binance, because we want to estimate trading cost on Binance, and then we want to take that trading cost estimation and compare it to Uniswap's, and then we want to show that whether our model predictions are correct, which is the main one is that higher trading cost on Binance means higher reserves are posted on the Uniswap's, and we want to show that in the data. So how do we calculate trading costs on Binance? I told you that price has a, there are two types of trading costs, permanent costs and temporary costs, right? So think of this as we only observe price, but in that price, there are two hidden terms which we don't observe, which is how much of that price is permanent change and how much of that price is temporary change. Permanent change is going to remain permanent, and if think of it as that if you want to look at next period's permanent change, it's a random. You don't know what it's going to be. Temporary change that has happened in the price is going to reverse itself. Like I said, if there is a big order, it's going to come back up, right? So there is a negative coefficient on that. So we don't know what MT and ST, which represents permanent and transitory components, mean. But we have some idea of what drives them, right? So we know that ST is driven, the temporary is driven from what prior period ST was, plus trading activity, trading volumes that are taking place. We also have a theory that permanent change or permanent price is a function of unexpected trading volume. So things that are not expected usually have information embedded in them. And how do we do that? We basically run a regression of volumes to prior volumes so that we look at a pattern, and something that doesn't fit in the pattern, we say that that is driving permanent change. So now we have this equation where we have change in price, but and then we can do another regression equation where we take change in price and we look at the volumes and just do a regression and estimate its coefficient. What we are interested in are two parameters. One parameter is this C parameter, and the other one is this kappa parameter. Kappa parameter is actually the permanent parameter of permanent change, permanent trading cost, and C is the parameter for transitory change or liquidity related price impact. So what we can do is we have on both sides we have same left hand side of the equation. We have delta PT here and delta PT over there. Then there is a little bit of algebra, and from algebra we can estimate these kappas and C parameters. Anyway, the bottom line is we do a regression of price to trading quantities, and then we can estimate these kappas and C parameters. So this is what we did in this paper. We applied that to data, and we looked at Binance data until October 2021, and we looked at commonly traded pairs. Why October 2021? Because that time version 3 started becoming prominent. So we wanted to restrict our data to version 2, Uniswap version 2. So that's why we cut that data window off. We looked at commonly traded pairs. We took all the commonly traded pairs and we measured, we got Uniswap, burn, mint, and transaction quality, queries from Dune Analytics. And we selected common pairs that met at one criteria, which is that in a 1 hour trading window, at least 30 Uniswap transactions actually took place. So that is our cutoff criteria. So and we got at least 100 hours of sample data in meeting this criteria. At least 100 hours where 30 Uniswap trades took place within an hour. And from there we selected 5 token pairs that were commonly traded. Then we calculate reserves, we manually reconcile that reserves are correct so that we assure that the data is right. Here's some of the things I want to show you about our 5 pairs. We have diversity of trading volumes here. We have ETH to USDT, Link. As you can see, some of these pairs have very high Uniswap activity versus Binance activity, whereas some have a very dominant Binance activity versus Uniswap activity. We also find pretty big variation in slippages, means actively traded. There's been a variation in active trading that is taking place on Uniswap. Now, here's the report card. Report card of which one has a higher trading cost and which one doesn't. So how do we calculate this? We look at slippage. Now slippage is for a certain average trading volume, and that is the ETH equivalent trading volume, right? And then we estimated our Binance trading cost compared. So the way the model works is, think of this to interpret this is this. If you're looking at Link, I'm sorry, this is showing up differently in this format. But if you look at how much of price change was permanent for 1 ETH of trade on Link to ETH contract on Binance, it was 0.0166% of price change was permanent. 0.008% of price change was temporary. If you combine the two, for 1 ETH of trading, the permanent and temporary combined price change or the trading cost was 0.0174%. 0.0174%. Okay? The slippage obviously is lower because obviously the big thing we are not putting in here is the fee, which is 0.3% on Binance. But if you think about this, how do I compare to apples? I have to look at ETH equivalent cost on Binance. So on average, 9.64 ETH worth of trade was taking place on Uniswap. And on average, 1 ETH trading cost 0.0174% change in price on Binance. So just scaling it up to 9.64%, we are assuming linear here. That means that the Binance trading cost for 9.64 ETH trade is 0.18%. Okay. Now, if you add 0.3% of fees on top of this, then you're basically saying that, you know what, Binance is probably more efficient when it comes to Link, to ETH. But for Aave and for LRC, you're seeing that actually Binance cost is less, is more expensive. It's more expensive to trade on Binance compared to Uniswaps. And Mana is also, closer. So this is our summary stats of what we've discovered in terms of comparing trading costs. Now, going back to our model parameters and what we are, the things that we are looking at in this paper are predictions. Our prediction would be that reserves will be posted based on trading cost. Higher the trading cost, more reserves will be posted. So we should expect a positive relationship between reserves and lambda. We have broken this down into kappa and C. And then this third specification here is the interaction terms of Binance minus reserves times lambda, telling you which effect is prominent. So in this case of ETH, as you can see, Binance minus reserve price is negative, although it's not significant. But the lambda, which is the transaction cost on Binance, is driving provision of reserves on Uniswaps. Slippage is invariant. As you can see, the kappas and psi have no significant relationship with slippage. And then when there is more trading activity on Uniswap, it is at the same time there is less informed trading that is taking place in Binance. Link has a different situation. Here, the difference between Binance and reserve price is actually the dominant factor that is causing reserves to increase. LRC, similar patterns. We could not find any significant relationship in LRC and Mana. Sorry, Aave was similar pattern. So here's the conclusion of this paper. First of all, we do find Uniswap provide competitive alternative to Binance, where trading cost could be advantageous. Meaning there is a high trading cost on Binance would tend to increase reserves in posting in Uniswap. So for practitioners who are trying to establish Uniswap liquidity pools, where would you create focus there? You will create focus more on contracts that have a high Binance trading cost. And then the other things are, I'm sorry I don't have time, but the other things are pretty much what we predicted in our model and we show in data that that's what happens. Thank you.